math induction, what we're trying to do is prove something like a formula. So let's look at a real basic one. 2 plus 4 plus 6, dot, 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 dot. So 2, 4, this is, what kind of series is this, by the way? I'm adding 2, adding 2. Which kind? Arithmetic, because it's adding the same each time. So the formula is 2 times n. So if the first term is 1, 1 times 2 is 2. Second term is 4, 2 times 2 is 4, and so on. So this is the generator generating the terms. This is the sum equation. And I think this formula is going to work this way. If I wanted to add the first 2 terms, what do they add up to? 6. If I wanted to look at the sum of the first 2 terms, I think I'm going to take n, which is not 1, but 2, and I'm going to say that this is going to be 2 times 3. Is 2 times 3 6? That worked. Whew, that was lucky. Let's try n equal to 3. Okay, I think it's going to be 6 times, or 3 times 4. What is the sum of 2 plus 4 plus 6? First 3 terms. What's that going to be equal to? 12. Is that 3 times 4? Okay, good. What do you think for n equal to 4, when I put in an 8 here, what do you think that's going to be equal to? 20? 4 times 5? So it looks like this formula works. But how do we know it works for everything? Into infinity. Well, we don't want to check every one of them. I don't have that much time. So what we're going to use is we're going to use this proof that's pretty cool, but it's going to be annoying at first. And it's called math induction, and it has 3 parts, 3 steps. Step 1, let n equal to 1. Step 2, let n equal to k. And it's going to seem like a dumb step because nothing's going to seem to happen, but this is my assumption step. And then you're going to have step 3, which is n equal to k plus 1. Now, I like to attribute this to, I'm going to prove that this formula works for everything, like climbing a ladder. How do I prove that I can climb a ladder? What do I have to do on that ladder? What's the first thing I got to be able to do? I got to make that first step. So step 1 is n equal to 1, the first step. Then I need to be able to go anywhere on that ladder, n equal to k, and take a second step. And so that's what's happening between these. I'm somewhere on the ladder, I'm taking the second step. If I can take the first step, and then I can take any consecutive step after that, I can prove that formula works, and I don't have to check everything into infinity. Whew, that's a lot. Well, let's try it. Let's try it with this one. We're going to do it. We're going to check this one out. I think that for this one, I wonder if I can just go to a blank slide. Do I have a blank slide here? I can make one. I'm going to do it. Would you go to a blank slide, and we had 2 plus 4 plus 6 plus dot, 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 plus 2 n equal to n times n plus 1. That's what we think it's going to be. All right. In step 1, we think this is the formula. So we're going to check let n equal to 1. Okay, let's do it. What is 1 times 1 plus 1? What is that? 1 times 2 is 2. Is that equal to the sum of the first step? Yes. So therefore, you're going to go right, therefore true for equal to 1. Everybody do that, please, with me. So you have 1 times 1 plus 1 equals 2. And maybe a smarter way to write it would be 2 is equal to 2. Therefore, this is a shortcut for therefore. 3 little triangle dots. True for n equal to 1. Yay, we're done with that step. Let's do step 2. Let n equal to k. Now this is going to be your favorite because all you have to do is say 2 plus 4 plus 6 plus ... plus 2. Instead of n, you put k. That seems like a waste of time, doesn't it? But this is your assumption step. You're going to use this in the future. Future being right now. Step 3. So we took our first step, and it worked. Now we're going to go somewhere, n equal to k, and we're going to take the next step. Let n equal to k plus 1. Now this is where it gets good. Okay? We have 2 plus 4 plus 6 plus ... plus 2k. Do you agree with that? That's what we had before, n equal to k. And then we're going to take another step. 2 times k plus 1. That's the next step. So I'm going to write a little note here. This is my last step. Last step. Now I'm going to take the next step. What should happen to this? What should happen to that? What should happen to this if we... Shouldn't this get bigger by 1? So this should grow by k plus 1, k plus 1 plus 1. So here's what we did. We were k plus 1, k plus 1. And what we did is we took this and we grew it to k plus 1, k plus 1 plus 1. So on the right here, this should be k plus 1 times k plus what? 2. Yeah. So this is what we need to show. We need to show this. We need to show this here. Mitch, you came at a tough time. This is a... But you're going to get it. You're going to get it. Did we lose your desk? Yeah, we'll get that. We'll figure this out. So this here can be replaced with what? What can this be replaced with? What can I substitute? What can I substitute this with? Turn to your neighbor. Tell them what you can substitute this with. Go. Can we replace? What can we replace 2 plus 4 plus 6 plus ... What can we replace it with? You got it. K times k plus 1. So this is going to be replaced with k times k plus 1. And then this is going to be 2 times k plus 1. Now we want to show that this and this are equal. What can I factor out of both of these? K plus 1, so I'm going to do that. What's left here, if I pull out a k plus 1, what's left? K, and what's left here? 2. Guess what? Therefore, true for n equal to k plus 1. You might be saying, what just happened there? Algebra. Algebra just happened. But what we did is we said 2 plus 4 plus 6 plus da 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 plus 2k is equal to k times k plus 1. That's what we started with. That was our assumption statement. Then we added the next term, so this 2k, we just replaced it with 2k plus 1, 2 times k plus 1, but we still kept all the rest of that. Then we grew the sum equation, because if you take the next step, your equation is going to get bigger, hopefully by 2k plus 1. Well, we're going to prove that. K plus 1, k plus 1 plus 1, and then when we replace that yellow with k times k plus 1, we could do the algebra to show that the left side equals the right side. Now, you're not going to like this, but we are not done quite yet. We have to do a big therefore statement. Would you write those three? Therefore, now you just restate what we did before. Since true for n equal to 1 and n equal to k plus 1, the equation works for all n greater than or equal to 1 by math induction. That is a proof by math induction.